Hi, I'm Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing the method of images technique for solving electrostatic boundary value problems. In the previous lecture, we talked about the uniqueness theorem, and essentially the idea is that if you found the solution to Laplace's equation, which is in fact what we proved, or to Poisson's equation, and the boundary conditions were satisfied, then you were guaranteed that you found the one and true solution. I mentioned that a technique for solving electrostatic boundary value problems could be taking a wild guess. And if your wild guess satisfies Laplace's equation or Poisson's equation and the boundary conditions, then you are guaranteed that your wild guess was in fact the correct solution. Now, that's not really a good approach to solving electromagnetism problems. However, with method of images, although it's not a wild guess, there's a bit of artwork or intuition involved. So in other words, it's not simply a question of being given a set of steps to follow, which you follow, and you arrive at a solution. There's a little bit of intuition. You're using your understanding of the behavior of these systems to guide you to the right solution. So basically, the best way to understand the method of images is just to dive right in and show you an example. The first example I'm going to show you has to do is basically the one that everybody does when you first talk about method of images, and that is when you have a point charge in the presence of an infinite grounded conducting plane. So basically the problem here is that you want to determine the potential due to the system. Okay? And we're seeking the potential above the grounded conducting plane. What happens below it doesn't interest us. And recall that whenever you have a plane that's grounded or any kind of conductor that's grounded, that means the potential is equal to 0 there. So we want to know what's the potential in this region of space. Now, this looks like it might be kind of a tricky problem. We figured out what the potential was due to localized charge distributions in an earlier lecture, and to potential due to a single point charge. So how do we combine both of these together? Basically what the method of images technique is that I'm going to figure out some image charge such that I can replace this conducting plane with it. And as long as I meet the same boundary conditions, in other words, if k is equal to 0, s equals 0, then I found my solution. Okay? So where do I start? How do I actually start writing down an expression? Your first inkling is, well, you know that potentials obey the superposition principle, then you must have a contribution to your potential due to this point charge. Seems like a reasonable thing to say, and in fact, that's correct. Potential due to this point charge is q over 4 pi epsilon naught magnitude of separation vector r minus d. So I'm going to place my charge d at distance d above the conducting plane, and we'll call this the z-axis. But there has to be some other term here, right? Because, well, it's true for a single point charge isolated. Its electric field lines radiate outwards, like so. But we're in the presence of a conducting plane, so these field lines are going to be bent, right? Because electric field lines are normal to the surface of conductors. So field lines are going to look like this. They're going to radiate outwards from Q, but they're going to impinge normally onto your conducting plane. So I have this term, but I've got another term as well that gives rise to this distorted field, if you will. And I'm going to call this second term some function f of basically of your observation point and wherever the source is, in this case, where the image charge is. So this is my original point charge, and this is the image charge that basically is going to replace this conducting plane. And here's where intuition or your understanding of the behavior of particles comes into play. When we discussed potentials, we calculated potential due to a single point charge, 2 like charges, and also 2 unlike charges as well. 2 unlike charges of equal magnitude. And the thing that, if you'll recall, the potential due to both of those charges along the midplane vanished. So basically what I'm going to do here is I'm going to replace this plane by some point charge down here. Some Q prime and some D prime. Now bear in mind these are not actual charges, okay? They're image charges. But I'm going to figure out what magnitude the image charge has to have and where it has to be located as well in order that I wind up with V equals 0 here. Since this is an infinitely large plane, reasonable choice for my location, my image charge would be here. Also a distance d away. And again, thinking back to our problem with calculating potential due to 2 unlike charges of equal magnitude, you make that a minus q here, then this potential line here will be equal to 0. So placing this conducting plane by an image charge, q prime, over 4 pi epsilon naught magnitude separation vector r minus d prime, but we reasoned that this image charge has to have magnitude q, it's going to have the opposite sign, and it's also going to be located along the z-axis, a distance d away from the midplane, or d, a distance d below the xy plane, if you want to look at it that way. Okay, so I'm going to go ahead and write these out in terms of the square root of the sum of the squares. So this will be square root of x minus x squared plus y squared plus z minus d squared minus q over 4 pi epsilon naught x squared plus y squared plus z plus d quantity squared. And I'll see immediately if I just substitute in z equals 0. V equals 0, right? Because this term, last term, will be just d squared, and likewise in my second term over here. And I have q and minus q, so those two terms cancel out on z equals 0, so no potential 0 there. By the uniqueness theorem, I'm guaranteed that if I find a solution that satisfies Laplace's equation or Poisson's equation and satisfies the boundary conditions, I am guaranteed that I found the one and true solution. So that's how you do the method of images technique. There's some other information we can extract from this system, such as what's the surface charge density, what charge is induced on this plane, and things like the force between this charge and the conducting plane. So we show you how to calculate those. In order to calculate the surface charge density, I'm going to make use of the boundary condition that we derived also a few times ago. In other words, the electric field above minus electric field below is equal to sigma over epsilon naught. It's sigma that we want to solve for here. I'm going to erase this to give myself a little bit more room. Okay, the electric field below is going to be equal to 0. Right? It's on the other side of the conducting plane, so it's just 0. What about above? Well, the electric field above can be found because we know what the potential is above, right? The boundary condition becomes the partial derivative of v with respect to normal is equal to sigma over epsilon naught. And remember, there's just a discontinuity in the normal components of the electric field. The tangential components vanish, or actually the same. So what's the normal in this case? Well, the normal to this plane is just going to be pointing in the positive z direction. So I'm going to take the partial derivative of v with respect to z here. And evaluate it at the z 0 plane. Both of those terms have in common the factor of q over 4 pi epsilon naught, so I'm going to pull those out outside. And the first term gives me minus 1/2 times 2 times c minus d over x squared plus y squared plus c minus d squared, all raised to the 3/2 power. My second term, when I take the derivative with respect to z, minus 1/2 times 2 times z plus d all over x squared plus y squared plus z plus d squared, quantity squared, all raised to the 3/2 power, and this is evaluated at z equals 0. These, we have two minus signs up here and two minus signs over here. We have 1/2 times 2 in each of these terms. So if I add both of these up, I'm going to get a factor of 2. I have minus q over 2 pi, and the d, and also in my denominator, I have x squared plus y squared plus z squared, all raised to the 3/2. This is the surface charge density that is induced on the plane by the presence of a point charge. So let me just state that again. It's minus qd over 2 pi times x squared plus y squared plus d squared raised to the 3/2 power. I want to figure out what charge is induced on the plane. So basically that's just a question of integrating the surface charge density over the entire conducting plane. You can actually take a wild guess as to what it might be. You can answer that question in 5 seconds, but I'm going to go ahead and do the math anyway. And it's more convenient to do this problem in polar coordinates, so I'll replace the x squared plus y squared by s squared. I'll integrate from 0 to 2 pi, and 0 to infinity, and my surface element the s ds dt, and sigma is minus qd over 2 pi and s squared plus d squared raised to the 3/2 power. 2 pi I can integrate immediately. That just will give me a 2 pi in the numerator, which cancels in the denominator. I'll put minus qd out. Also, I can integrate this s over s squared plus d squared immediately. That's just going to give me minus 1 over the square root of s squared plus d squared, evaluated from 0 to infinity. At infinity, this term is just going to vanish. At 0, however, I'll wind up with minus qd minus 1 and minus 1 over d. And my answer is minus q. That's the charge that is induced on this conducting plane by the presence of a point charge. So that makes sense when you think about it. Since my image charge is minus q, it seems like, well, you'd also have to have minus q there, and you do. Okay? You might want to know what the force is between this charge and the conducting plane. So I can figure that out by calculating the force between these two, the real charge and the point charge. The force between my charge and the conducting plane, just going to act along the z-axis. It's going to be an attractive force because this is positive and this is negative. It's minus q squared over 4 pi epsilon naught times distance between those two charges squared. So that's times 2D quantity squared. Okay. The last quantity of interest is the work, or the energy associated with the system. And here you have to be a little bit careful. The way I like to calculate it is basically using this expression. Work is equal to the force times the displacement over which force acts. And in this case, we're bringing the charge into some point D from infinity. And in this case, we can write this as infinity to D minus Q squared over 4 pi epsilon naught over 4z squared. One other thing too, we gotta be careful here because remember, we're having to do work against the field, okay? So we're gonna use the opposite sign for the force between the charges. And this will be Q squared over 16 pi epsilon naught D. Okay? So basically, I'm just using my force expression and remembering when we're calculating work, we're doing work against the field, so it's the minus sign of the force that we have here. So that'll be Q squared over 4 pi epsilon naught. This is the force between the two charges when this charge Q is the distance D away, but remember, we're bringing it in from infinity. So we're going to replace that by a Z, and then we're going to integrate from infinity up to D, and that gives me Q squared over 16 pi epsilon naught D. And that's how you calculate work. If you make a naive assumption and say, well, gee, I can just calculate it directly from the charge and the image charge, remember, this example encompasses the entire region space. The problem that we're solving, however, is limited to the region above the plane. So in fact, you'd wind up with twice the amount of energy. So this energy associated with this configuration is actually different from this one over here. So you have to be careful when you're applying the image charge to not take things too far. Okay? So we figured out what the potential is. And we figured out what the surface charge density is. We figured out the total charge induced on the plane, which is minus Q. And we figured out what the force was between the charge and the conducting plane. And last but not least, we figured out the energy associated with the system. Okay? Now this is, as I said, the first problem that anybody ever starts with. But let's say you get a little bit more complicated system here. Let's say we just have a stack of charges, row of charges, if you will. Q, 2Q, 3Q, and located different distances away from the conducting plane. How do you figure out what the image charge is? Well, once again, you want to think of the superposition principle of the potential. We can figure out what the effect the conducting plane has due to the field of this charge. In other words, you're going to wind up with a minus Q down here, minus D, and then figure out, well, what's the effect of this 2Q on this system. So that's going to be minus 2Q, locating the distance 2D down. And we have our charge, well, let's change things up, let's make that a minus sign. You got minus 3Q up here, located distance 3D away. Well, your image charge is going to be 3Q, and it's going to be located in 3D below the conducting plane. So you can just sum up charges, right? Because the potential obeys the superposition principle. What if you don't just have a conducting plane? Let's say that you've got the intersection of two conducting planes. And your charge Q is located at distance A away from the y-axis and A away from the z-axis, I should say, and a distance B away from the y-axis. What's your image charge going to look like? In fact, in this case, it's not going to be a single image charge that suffices. You're going to have to have a set of charges such that the potential here is set equal to 0 and the potential along here is equal to 0. And bear in mind, in this case, you're looking for the solution in upper right quadrant. You can never have an image charge in the region of space over which you're solving. So over here, our image charge was below it. So we were solving in the region above the conducting plane z equals 0, z greater than 0, and our image charge was therefore below the conducting plane. Likewise for over here, we had a set of charges. All our real charges were above the plane, and our image charges were located below that. Now in this case, when you have the intersection of two infinite conducting planes, you have a nice little corner here. We're looking for the solution in the upper quadrant, so your image charge is actually going to be over here. So just think about the symmetry of the problem and use that as a guide to figure out where are they going to be located, okay? And you can go on and figure out such things as charge-induced, force on charges, and so forth. So those are good exercises to work through. Another kind of problem to solve is what if you have point charge in the presence of a conducting sphere? How do you go about solving that? So let's do that one next. Here's my conducting sphere. That has radius r. And I have a charge q, some distance d away from the center of the sphere. My conducting sphere is grounded, so therefore d equals 0 there. And I want to figure out what image charge can I figure out to such that the potential on the surface is equal to 0. So in other words, I'm going to replace this problem and let's change this up. This is a spherical surface, and I want to solve the potential outside that sphere. The charge is out here, so my image charge is going to have to be somewhere inside. Okay, where exactly? Well, once again, you want to use your understanding of symmetry. Really, the only place it can be inside the sphere is along this axis that joins charge q to the center of the sphere. I'm going to actually draw my image charge over here. It's going to be somewhere here. We don't know what magnitude it has yet. And we don't know how far it is from the center of the sphere. That's what we're going to determine next. so my VR is due to that first point charge, Q, over 4 pi epsilon naught r minus d plus Q prime over 4 pi epsilon naught r minus b. And it's Q prime and b that we want to solve for. Now, I can't just simply assume, well, Q prime is going to be negative. That doesn't make sense, because if you pull this charge further and further away from the conducting sphere, you'd expect the distortion to this to become, to the field of Q to become smaller and smaller. So this there's no way can be D inside here. It's not enough room anyway. Let's see what else. Well, we're evaluating at some arbitrary point R from the origin. And it's instructed to replace these again by their square root of the sum of the squares. First term we'll have r squared plus d squared minus 2 times the dot product of r and d plus q prime over 4 pi epsilon naught r squared plus b squared minus 2 times the dot product of r and b. Now remember what dot product is. It will give you the magnitude of those two vectors times cosine of the angle between them. Well, these guys lie along the same axis, so therefore the angles between these two vectors, r and d and r and b, are going to be the same. First term becomes q over 4 pi epsilon naught r squared plus square root of r squared plus d squared minus 2rd cosine theta plus q prime over 4 pi epsilon naught square root of r squared plus b squared minus 2rd cosine theta. Okay, so what next? Well, here's where we're going to apply our boundary condition. We know that b of r is equal to 0. The only way these two terms can possibly cancel each other out is if these radicals are proportional to each other. Figure out, well, what must B be? You know what D is. You know what. We're evaluating this at the radius. So B is going to have to be written in terms of D and R. Okay. And if you think of any simplest two expressions. B is a distance, so therefore, however you write this in terms of R and D, has to also be in terms of the distance. So, two possibilities here. We can have B is equal to R squared over D, or and I'm guessing here, by the way, is equal to 2 over R squared. Well, we're looking for the exterior solution here. So I'm going to pick the first one. guess that my distance b is proportional to r squared over d. It has the right units after all. Doesn't have a cosine theta, can't. I'm going to substitute this in here. So therefore, my second radical here becomes, we're evaluating this at the radius, so we have square root of big R squared plus b squared minus 2rb cosine theta. I have guessed that b has a form of big R squared over d. And I've made that substitution. As I said, there are only two simple ways of writing b in terms of both r and d. And we're looking for the exterior solution here, which is why I chose this one. And I'm going to pull r squared over d out of each of these terms. Now we just pull r over d out of each of these terms. Pull r over d out. I wind up with r over d times square root of d squared plus r squared minus 2rd cosine theta. That's exactly what this radical has evaluated at the radius. Therefore, if I assume that q prime is equal to minus r over dq, this will vanish at the surface of the sphere, and hence that's the solution. That's my answer is, if I place my image charge at this distance away from the center of the sphere, r squared over d, and I've substituted in b in here, and I've evaluated this radical at the radius, and substituted in r squared over d wherever b appears. And I said, okay, I'm going to pull this r over d out. So I pull it out of each of these terms. And I wind up with d squared plus r squared minus 2rd cosine theta. So this term now is proportional to this term, which is what I needed to have in order for this to vanish. Therefore, if I set, or assume it's probably not the right word, but if I set q prime is equal to minus r over dq, then this vanishes at the surface of the sphere. So therefore, my v over r is equal to, or rather v as a function of r is equal to q over 4 pi epsilon naught square root of r squared plus d squared minus 2rd cosine theta minus qr over d all over 4 pi epsilon naught square root of r squared little r squared plus big R squared to the fourth over d squared minus 2r r squared over d cosine theta. And that is your solution. So let me just plug in numbers just as a check. V of r as a function of r. I'll pull q over 4 pi epsilon naught out because both terms have that factor in common. So the first will be 1 over big R squared plus d squared minus 2 big R d cosine theta. Minus q r d over r squared plus r to the fourth over d squared minus 2r cubed over d cosine theta. If I pull r and d out of the bottom term, that'll cancel with the 1 in the numerator, and I'll wind up with 1, basically 1 over all this stuff minus 1 over all this stuff, and that's equal to 0. And that's how you solve the problem of a point charge in the presence of a charged, or grounded conducting sphere. Okay? So this is a little bit harder to arrive at an answer here than with the conducting plane. And you can go in and figure out what's charge induced on the sphere, what's the force of attraction between the charge and the sphere as well. Another interesting problem you can figure out, well, we said it was grounded to begin with, but let's assume that it wasn't grounded. Let's assume that there in fact was a potential V naught initially. And I want to figure out what's the potential in the exterior region. Okay. Once again, you want to make use of the superposition principle. Why? Because we already solved the problem when the sphere is grounded. Now we have to figure out how do we make the charge, or how do we make the sphere have potential V naught. We'll use the solution I had before. That still holds. Then I'm going to have another term that accounts for the potential. So this makes the sphere grounded. And we want to figure out what's this other charge such that it makes the sphere have potential V naught. We solved this problem already. We can set that aside. My superposition principle, my sphere is basically, or my my sphere is grounded initially, so that's one part of it, and now my sphere has potential V naught. So notice I've written Q double prime, and we're writing it most generally as R minus A. We need to reason out where this charge is going to be. Well, whatever that charge, second image charge is, it can't distort this potential, okay? So the only place it could possibly be where it won't distort the answer we've already obtained is if I place my image charge at the origin. So therefore, my third term here is going to be q double prime over 4 pi epsilon naught r. Now, we want to apply our boundary condition that if r equals the radius, we have q over 4 pi epsilon naught, magnitude of the separation vector between capital R, the radius, minus d, plus q prime over 4 pi epsilon naught, magnitude of the separation vector between r minus b, and plus my new term that will account for the sphere having potential v naught. So it's q double prime over 4 pi epsilon naught big R. Well, I already solved this problem that these two guys vanished at the surface of the sphere. That was precisely the problem we solved before. So therefore, I can solve this for q double prime. Q double prime is equal to 4 pi epsilon naught radius of the sphere times the potential v naught. So my solution is modified by the addition of this one final term. It's just going to be v naught big R over little r. It's possible once you've found one solution to work off and figure out more complicated configurations. Back when I was a student, one of the things that I would say kind of annoyed me when I was learning about method of images is that it seemed like, well, it's a really interesting technique, but why is it not more useful than, say, something like separation of variables? And the answer is you don't get to this. The reason why this is important in undergraduate EM. Basically, this really sets the stage for the Green's functions method, and that's a very powerful technique for solving electrostatic boundary value problems. And you'll get to that in graduate level electromagnetism. So this really here, what I've shown you, is just the beginning. Method of images, remember, just boils down to finding an image charge that satisfies certain boundary conditions. And by the uniqueness theorem, you guarantee that if you find a solution that satisfies boundary conditions, you are guaranteed that you found the only solution. And once you start off, you find a solution to a simpler problem, you can build upon it and find solutions to more complicated problems. Well, this concludes the lecture on method of images. Next time around, we will get into the separation of variables.